So suppose we have items of weights W1 through Wn and values V1 through Vn. Let Dij be where Aij is a subset of the first I items whose total weight is j or less, and whose total value is as great as possible. Now, if the total weight of the first I items is less than the capacity j, we'll just let Aij be that set of the first I items. This corresponds to the possibility that the knapsack can contain all available items. But if the total weight of all items exceeds the capacity, there are two possibilities for the optimal knapsack. First, we can simply ignore the additional item, so Aij is I-1j. That is to say, the optimal knapsack where we have I-1 items and capacity j. Or we can add the ith item with weight wi to the optimal knapsack with capacity j minus wi. So Aij is that set together with the ith item. So suppose the knapsack has a capacity of 8 pounds and can be filled with items with weights 1, 3, 5, 7, and 8, and values 10, 20, 40, 45, and 75 respectively. Which selection of items will maximize the total value of the items in the knapsack? So remember, nothing counts. Suppose our weight limit is 0. Then we can't include any objects. So our optimal set has value 0 with no items. We'll record this way. So here's our value, and here's the set that produces it. And since this is true, regardless of how many items are actually available, we have di0 equals 0 null set for all I. Now suppose only the first item is available. We already have d of 1, 0. If our capacity is at least 1, we can include the first item, which has value 10. So d of 1, 1 is... And since it's the only item available to include, this means d of 1j is going to be the same for all j greater than or equal to 1. Moreover, since the weights of our items are in order, it's the only item that could be included in a knapsack with a weight limit of 1. This is why it's convenient to have our items by weight order. So d of I1 is also 10, 1 for all I greater than or equal to 1. Now suppose the second item becomes available. This item has weight 3 and value 20. We can't add it until the weight capacity is at least 3 pounds. This means d of 2 has to be... Moreover, since all later items have weight greater than 2 pounds, they can't be considered for inclusion even if they become available. So d of I2 is also 10, 1 for all I greater than or equal to 2. Since the total weight of all currently available items is 1 plus 3, 4 pounds, this means we can include both in any knapsack with a capacity of 4 or more pounds. So d of 2, 4 includes both and has value 30. And since all remaining items have weights 5 or more, none of them can be considered for inclusion even if they were available. And so d of I4 is the same for all I greater than or equal to 2. Finally, if these are the only items available, then increasing the weight capacity of the knapsack won't change anything. So d of 2j is going to be for all j greater than or equal to 4. This leaves d of 2, 3. So at this point we have to make a choice. We can either ignore the new item using the D1, 3, 10, 1 knapsack, or we can add the new item to the knapsack with a weight capacity of 3 minus 3 is 0. This would be the D200 null set knapsack, which would become a 23 knapsack. Since this is more valuable, we'll let D of 23 equal 23. And again, since all remaining items have weights greater than 3, none of them could be considered for inclusion, even if they're available. So D of I3 is also going to be 23. The third item has weight 5 and value 40. Note that we can no longer include all the items of the knapsack, since 1 plus 3 plus 5 equals 9. For the knapsack of capacity 5, we can either ignore the new item, giving us the 2-5 knapsack, or we can add the 5-pound item to the 0-pound knapsack, which gives us the 45 knapsack, which has greater value. And so D of 35 is that 45 knapsack. And since the remaining items have weight greater than 5, this is going to be true even if those other items become available. For D36, we can either ignore the item, giving us the D26 knapsack, or add it to the knapsack with capacity 6 minus 5, 1, namely D31. This would give us a 51-5 knapsack, which has greater value. So D of 36 is going to be 1-5, and since all remaining items have weight greater than 6, then for D37, we could either ignore the new item, giving us the D27 knapsack, add it to the knapsack with capacity 7 minus 5, 2, namely, again, this would give us a 51-5 knapsack, which has greater value. And so D of 37 is, and likewise D of I7 is going to be this for all I greater than or equal to 3. Or is it? Since we do have an item of weight 7, we might be able to include it when it becomes available because our knapsack has capacity 7. So in this case, we cannot extend the optimal selection. Finally, for D38, we can either ignore the new item or add it to the knapsack with capacity 3. Again, adding it to the latter gives us a 63-5 knapsack, which has greater value. So D of 38 is, and since there are additional items with weights less than 8, we can't extend this result downwards. The fourth item has weight 7 and value 45. If the weight limit is 7, we can either ignore the additional item and use the D37 knapsack, or we could add the weight 7 object to the knapsack with weight capacity 0, which would give us a, since this has a lower value, we'll use our original knapsack. And again, since all remaining items have weight greater than 7, none can be considered for inclusion in this knapsack even if they become available, and so for D of 48, we can either use the D of 38 knapsack or add it to the weight 1 knapsack. This would give us a 55-17 knapsack, which has a lower value, so we'll keep D48. Again, since we have an item of weight 8, we can't extend this value downward. The fifth object has weight 8 and value 75. For D of 58, we can either ignore the fifth object and use D of 48, 63-5, or add it to the weight 0 knapsack D of 40. This would give us 75-8, which is greater, so D of 58 is 75-8.